What is an inductor? What is it?
A physical component.
Yes! You need to be familiar with these terms, as guess what the yellow state. Know the characteristics, solve circuit parameters. So it's the physical component. And it kind of looks like, what? Well, wire, isn't it? Okay, straight piece of wire. It has what kind of property? It has to do with inductance, but we can say a piece of wire has inductive properties. Because it opposed to a change in what? Yes, that's a magic word for inductor. Current. Opposed to the change in current. So the inductor is a physical component that's opposed to change in current. And we discussed, yes, change or variation in current. Is that magnetic field that's created around, when you just think about a straight piece of wire or a coil of wire, because there is a big difference between the two, but it exists in both because they have inductive properties. So we want to take advantage of that magnetic field, electromagnetic field expands and collapses, because the energy is stored in that field and gets released to the circuit. How often? It's like continuous, isn't it? Because 60 hertz to the electronics world is what? Kind of slow, but to us it's still fast, so it's constant. So inductance would be what? I would describe that.
Characteristic of an inductor that opposes the change in current.
Yes, here's the thing. Characteristic, you want to make sure you know both. Of a conductor or inductor, because they're both what? What are they both?
They both oppose the change in
Just wire, or one's straight, one's coiled, right? Coiled wire concentrates the energy more, doesn't it? That field. That's why we coil it. We want to concentrate the energy. Characteristic of a conductor or inductor, again, back to opposes the change or variation in current, because this right here, what's that stand for? Alternating current. When we say things like volts AC, well, we know it's the RMS value, but isn't that the whole package? Potential, current. So how do we know how much current's in a circuit, though? Like how much? How do we know how much current exists in just any circuit? When I have source applied, how much current's in the circuit? How do we know?
voltage divided by.
Well, yeah, Ohm's law, yeah, it depends on how much what opposition exists. That's how we know how much current. And we can calculate when we make those things. So there. Inductive reactance, also known as what? Yeah, X sub L, inductive reactance. It's going to increase, or if I decrease, it's the opposite effect. It's a multiplication problem, isn't it? It is. However much inductive reactance is in an inductive circuit or an RL circuit or RLC, how much it's going to oppose that frequency. And how much inductance is. And then, of course, we can use Ohm's law to help us find things like parameters of our circuits, such as like I total, voltage drops across inductor, those parameters. Yes, no, maybe.
Yes, sir.
Yes. So as far as the basic definitions go, pretty good?
Yes, sir.
They look really similar, but magic word's current. Now here's the thing. You look at all three of those terms, definitions. Do you see the word voltage anywhere?
No, sir.
No, sir.
So that might be a clue when we get into capacitors. We're going to talk about what? Voltage. And those definitions aren't going to have the word what in it.
Current.
So you see how it's really easy to, if you're paying attention, you can't screw up the difference between capacitance and inductance, or capacitive reactance and inductive reactance. You shouldn't be able to screw it up, but guess what? Let's do it! So pay close attention to this. That's why it's a good idea to stay the hell awake when I'm going over these things. Current, that's why I do this for you guys. In classes before, and I'll do it for classes in the future. Current, think about current when we're dealing with inductors. There's no word up here, word that says voltage. I don't see it. So how much have I elaborated on that? Quite a bit. It's to help you. Now there are some rules to solve certain parameters, because as far as the characteristics go, that's pretty much it. Is there anything else characteristic-wise about inductors? There's other things, but that gets into transformers later. But as far as inductors itself, that's about it, huh? It's described in your handout. There's a diagram there. Solve circuit parameters. We have some rules, don't we?
Yes, sir.
Series. What's rules for finding total, what do we call that L? What does that represent? Inductance. L sub T, total inductance in series. What's the rule as far as how we find it? What do we got to do? Add. What about XL total? If we want to find total inductive reactance, what do we got to do? All right. Hey. Parallel. What's the rule for total inductance? We have to reciprocate, and I'll just go 1 over L to indicate reciprocate. And X sub L total, or total inductive reactance in parallel, what we got to do? And I'll just go 1 over XL total like that, just to indicate we reciprocate. Hey, aren't those the same rules, just like resistors in series and parallel? It's the same thing. And then I sing a song about treating ohms like ohms to help you remember, especially when we get to capacitors, that you still, no matter what, resistors, inductors, capacitors, you still treat ohms like ohms. You add in series and reciprocate parallel. The opposition, that is. So when you take an exam tomorrow, remember these things. This is an easy exam. It really is. And I'm not saying this, I know all the answers, and I took the test already myself. No. It really is. If you applied yourself this morning in X and you found, after you got over the hump of just learning these new formulas, if you find or found last night that solving this circuit and these two circuits were pretty easy, ain't no about thing. Because that's what we're going to go over now. So if you can handle solving a series parallel inductive circuit, that covers the wickets, doesn't it? Right here for series and parallel, the rules, and actually applying it to solve parameters. To include Ohm's law, because I'm asking for I total. What about this series RL circuit? We've done plenty of these. This should be second nature now, series RL. And then this one's a what? Yeah, this is parallel RL series. And this one just happens to be a series parallel inductive circuit. So if you are able to solve these with ease, with very little difficulty, good. As far as inductors go, good to go. So now,